All right, welcome back to the Algebra 2 Semester A Unit 2 Graphing Polynomials Functions Tutorial Part 2. So we're going to start back up. I think I stopped right there on Part 1 of, at the end of slide 17, but we're going to pick up on slide 17. So remember, we're going to be graphing these polynomials and we're going to be given some type of verbal description for it. Or like I said before, in the previous tutorial, we learned about those zeros or those when it intercepts on the x-intercept. Not only that, we learned about the multiplicity of each zero. If it was had a multiplicity of an even number, it was going to touch the x-axis and bounce back. Or if it was raised to an odd, it was going to go ahead and go straight through. So the question is, we saw it in like graphically. Now what happens if we see it through a table? So this table right here is a polynomial function given as a table values. It is important to be able to identify key features from a table because sometimes this is all information we have. For example, in the data collection scenarios, data is usually presented in tables because it's collected by points. So we're going to go ahead and determine some of these key features strictly off of finding by looking at the table. So we don't have an actual visual description. We can put our own points and roughly estimate, but it's good practice to just go ahead and take a look at the table. So the first thing they're going to go ahead and consider is finding out when is it increasing or decreasing. So and the reason I'm clicking through here, because normally I walk you through it before we even touch the orange buttons. I wanted to see what order they want to go from here. But the idea that they're trying to analyze when it's increasing or decreasing is looking at the second column under f of x. So right here, we would start at 0, and then we go to 5.5. So 0 to 5.5, that's an increase. But then 2.1. So I'm going to stop right there. This is considered the increasing part. Now, 2.1 to 0, again, 5.5, like the idea of what I'm trying to do is, it's like I didn't want to draw it, but I am going to draw it. I'm more of a visual person than just by looking at the table. I need to get some idea of what we're doing here. So I have this point at 0, 0, then it's 1. Let's just say 5.5 is up here. And then it's 2.1. So let's just say like right here. Then it's 3, 0. Then we have 4, negative 0.7. 5, negative 1.2. And then it is 6, 3.8. So if I roughly draw out my polynomial here, I have this. It looks like it could be cubic, or at least with an odd power, because first I see that the right side is going up and the left side is going down. So remember, when the right side and left side go in opposite directions, we have an odd function. Now we count out our zeros as well. We have a 0, 0 at 0. We have it currently at 3. And there's a point between 5 and 6 that it also goes through a 0. So the idea that I'm getting here is that we're most likely have a cubic polynomial here. So the idea about the increasing part. So this area, it is considered increasing. Oops. Then we have a decrease, and then from here, we have another increase. So the values are increasing from 0 to 1. That's that first section here, which, I drew it kind of pretty wrong because we're limited only from the x-axis here. So from 0 to 1, and then from 5 to 6. So again, let me redo this because we don't know exactly what happens. I'm making that assumption that we are increasing more and more from there. So let me draw it there. So those little sections, the first one is from 0 to 1. The second one is from 5 to 6. Those are my only times my function is increasing. Now, when is it decreasing? It's from 1 to 5. So that area, we like to write it in interval notation. So let's just take a moment to write that out. So if it is increasing, so let me put increase. We are going to keep it now because we don't know if the polynomial is extended from 1. I can say that it could bounce and then go this way, or it could go straight down. We just don't know. So we're pretty limited on if there's what's going on beyond that table. Again, we don't have the function there. So it is going to be an increase from 1 to 2, or 0 to 1. Oops. 0 to 1. And then we have a break because it's decreasing. We only want to increase. So we're going to put a union for that jump. And then it would be from 5 to 6. Now let's go ahead and talk about the decrease. So as we're decreasing, it's the part that we didn't highlight, and that is starting at 1 and it ends up at 5 because that's when we have our turning point. So then we'll have parentheses 1 comma 5. Keep in mind they can't be brackets because brackets means it's exactly there. That's it. But remember, because especially right here, this 5, it's the border of where it switches from decrease to increase. So we have to be very, very careful with that one right there. Let's go ahead and take a look at the next one. The values of decreasing, that's what we discussed. That is from 1 to 5. Again, you can kind of already tell that there are there is 1, 2, or actually 3 zeros. Sorry. The thing is, this one was not mentioned. It's not listed there. Again, they're using from the x-axis only whole integers. And this one, we know it's between 5 and 6. But again, it's like I want to give you a proper way of like, all right, these are the details you can find, but it ultimately is going to depend on what you have. And like you're going to be limited to only certain key features to find for this case here. Let's take a look at this right here. So they are inside 18, they are still using the same table as before. They're identifying the zeros for us. Remember, the zeros are also, in other words, the x-intercepts. So how do I know I have an x-intercept in a table? Any x-intercept is going to be a number, comma, 0. So if I look for my zeros under the f of x, under f of x or the y column, right? I'm going to find my zeros. So that's 0, 0, and 3, 0. Again, those are the ones listed right here, the first 2 red dots that I have. Again, that was just a little bit rough estimation. Now there is another 0, and it's between 5 and 6. But here they only listed us the 2 main zeros there because that's what we can clearly see from the table. Remember, I drew it out to kind of help me visually see it. It doesn't hurt to draw it out. Again, you can kind of see I did rough estimates on the points, but we know that there's another 0 there. It's just not listed for us in that table. But that's where they're going to go ahead and discuss it. Again, sometimes it's like by reading the table, you're going to see the change 0, 5.5, 2.1, 0, then negative, and then to positive. Where did it go through my 0? They're also making that statement. You have another 0 between 5 and 6. But we kind of saw that picture is worth 1,000 words. Pictures are a lot more nicer, a lot more clear as well. So they're also going to go ahead and talk about the maximum and minimum range. So the lowest point was this one right here, which is at negative 1.2. The highest point is 5.5. So me even drawing these out, again, I just wanted to know roughly an estimate here. Technically, it does have no extension. We're pretty much blindsided on beyond 6, beyond the 0. So we're strictly limited to what we only have on the table. But you can kind of see roughly drawing it out, it doesn't hurt. If you can see it from the table, perfect. But I think drawing it out, even if it's just a rough estimation, also gives you a bigger idea, a nicer idea when you're being asked to go ahead and determine these values. But again, have you noticed that most of the time you're looking under the second column, which is the f of x or the y? Let's go ahead and move into slide 19. So it says to find the the extrema from the table of the values, we need to locate all of the relative maximums and minimums. Open the graphing tool and use the data tab to plot the points from the table. So we're gonna go ahead and open up this graphing tool. If it does right here. It takes a moment to load. It says your graph should show the extremas of 0, 0, 1, comma 5.5. A polynomial function will naturally have peaks and valleys. So there may be more. Okay. So how are you going to insert this data over here? You're going to click over here on the right-hand side for data, and you're going to, so the coordinates. So you can go ahead and take a moment, but I'll show you how to write the first 2 points. You'll type in these points 0, 0, 1, comma 5.5. You would go ahead and enter. So you're not going to enter parentheses. You'll type in 0 for under X, 0 for Y, and then it's 1, 5.5. And again, you're going to go ahead and continue on typing them in. You'll hit plot, and you should get a couple of them. The thing is, you're going to get a rough estimate to the very similar drawing that I had. And from there, you're going to be able to tell the hills. Now, keep in mind, it won't be attached with an actual line. They're just going to be dots. But even from there, you get an idea, a rough estimate of these points. But however, since the table does not provide a full picture of the function, these points are the best estimates for the relative extrema. We can use these points to approximate and interpret features of the function when only a table is given. So with a table, if you consider it, we're actually pretty limited there. Again, we're stuck between whatever they give us, and we can't see beyond that. You can even say like parameters that we're limited. Let's go ahead and take a look at this one on slide 20. Winter temperatures tend to be cold in the city of Johnston. The local weather station recorded the temperature over the course of one winter day in the table values, where T is the number of hours since the station opened. So we have our hours. They have been open for 1 hour. The temperature is at 6 degrees. They have been open for 2 hours already, and it goes down to 5, or down to 5, and continues. Which 3 statements, so we're not going to be selecting 3, are correct interpretations of this situation? So again, you can go ahead and draw it off, or we can just verify. The temperature is increasing from over the interval of 3 to 6. So if I look at specifically from 3 to 6, the temperature is increasing. So here's my 3 hour to 6 hour. Is it increasing? So I go from 0 to -2 to -1, then to 0. Is between those numbers, am I increasing always? So if it's true, you're going to select it. If it's false, do not select it. Let's take a look at the next one. The temperature reaches a relative extrema after 4 hours. So is it, remember that the relative extrema, it could be a maximum or minimum. Do I have a maximum or minimum at 4? So let me see. T hours equals to 4. I go, let's see, 6, 5, 0, then -2, and then up to -1. So if you consider it just like, again, like a rough estimate. Oops. Again, you're doing like, we're doing just rough estimates. If you like, it's 1, it's at 6 here. This is 2, this is 5, 3, 0, 4, -2, 5, -1, 6, 0, 7, -3. So we have something like this. Is this technically a maximum or minimum that we have right there? Because that is our 4, -2. Is it a point where it switches from increase to decrease or decrease to increase? It says the temperature is negative on the interval from 3 to 6. So if again we look at the interval from negative 3 to 6, 3 to 6, sorry, is this section right here from 3 to 4, 5, 6, is this section right there negative? True or false? If it's true, go ahead and select it. If it's not, don't select it. Now let's move on to the next statement. The temperature is decreasing from the interval of 1 to 5. So if I go from 1 right here to 5, we're going to focus again on the right side column. Is it decreasing? So I go 6, 5, 0, -2, -1. So if I go over here, 1, 2, 3, 4, 5. Is that whole section area right there to you decreasing? And then the next one is, oops, it says the range of the temperature. So remember, the range is talking about the vertical part of the graph. What's the lowest point? What's the highest point? So we consider our lowest point here. Give me a second. So again, the range goes from the lowest point to the highest point. So we consider what is the lowest number that we see here. So again, you can take a look at that by looking at that column. So again, the lowest point seems like it's right here, and our highest point is here. So what's the height of this number here? Oops. What's the height of our number here, and what is the height of our number here? If it matches to those numbers right there, you are all set. F of t again represents the y. Again, range is also in terms of y, or represents the spread between on the y-axis. Moving on to slide 21. So graphs of polynomial functions. Again, we're going to go ahead and take a look at graphs, but it says before we start, take a moment to review synthetic division and factoring methods. We'll need to use these tools to help us find the key features of our polynomials. So one of the most important parts is that we're most likely going to find, because we're going to go ahead and review synthetic division and factoring methods, is because we're going to go ahead and end up finding our zeros, or we're going to be given a polynomial and we need to find certain things. And what I mean by certain things, I mean the key features. So like x-intercept, y-intercept, and then we can kind of roughly graph it. We'll go ahead and take a look at that. So let's first start out with this one right here. So we are given the polynomial function p of x equals 18x cubed minus 63x squared minus 12x parentheses 2x minus 7. So what we're going to go ahead and do is, well, right there, we can kind of see if you were to multiply this 12x back into the parentheses, you're going to be left with 4 terms. Remember, we use grouping method when we see those 4 terms. Now, they did do an extra step for us already. They factored the GCF from the second set of parentheses. We need to factor the first pair. And that's kind of what they already did to us right here on this page, on this one here. So by taking a look, we just need to go ahead and factor out the JCF for 18x cubed minus 63x squared. So we focus on the variables first. The most that I can take out is x squared. And I can also see that both 18 and 63 are divisible by 9. So that's how they came down to this part here for us. Now we can still factor out the 2x minus 7. And I crossed it out so I can like kind of clearly see, but let me write this out here. Actually, yeah, let's write it out here. 2x minus 7, parentheses. And we're left with the front as 9x squared minus 12x. Now, if I focus per parentheses and see what can I factor out anything else, I look at my first parentheses and I'm like, all right, they both have an x. So I can factor out an x, and they're both divisible by 3. So I'm going to take out a 3x here. So 9x squared divided by 3x is 3x minus 12x divided by 3x is 4. And then again, we still have our 2x minus 7, which we know we can't factor out from either. So we stop right there. So I have my factored polynomial. I'm actually going to transfer it over here because we're going to go ahead and take a look at those next steps of what they did there. Okay, so now that we have that, the p of x already factored, I'm going to go ahead and clean this up a little bit here because now we can go ahead and figure out, once we have it all factored, we can actually find out our zeros. And why am I putting that the idea about finding our zeros? This does look a little bit different compared to the last tutorial where we were looking for our zeros. All the factors were really, really nice. So the question is, and also we knew a shortcut. In this situation and this example, we cannot apply that shortcut. So what we're going to have to do is take each factor separately. So this is each factor, right? 3x is its own factor. 3x minus 4 is its own. 2x minus 7 is its own. And we're going to take each factor and set them equal to 0. So the first one is 3x is equal to 0. You isolate x by getting rid of the 3 by dividing both sides by 3. X is equal to 0. We do it for the next one. 3x minus 4 is equal to 0. Again, you're isolating the x. So we'll get rid of the minus 4 first by adding 4 to both sides. And we'll have 3x equal to 4. Then we have 2x minus 7 is equal to 0. Add 7 to both sides. And this is 2x equals 7. I just realized I didn't even finish this one. I'm sorry. We divide 3 on both sides here. Let me take a step back. So then we have x equals 4 over 3. And here we'll divide by 2 on both sides again to isolate the x. And x equals 7 over 2. So now that we have these 3 zeros, and also if you think about it, look at the highest degree power here. It's x to the third power. So so the possibilities for this, right, is that we're gonna get 3 possible zeros. We could also get complex numbers. But unfortunately, you can't graph the complex numbers onto the graph because again, it doesn't exist. It doesn't touch the x-axis. Here we have our 3 zeros. It's at 0, excuse me, 4 over 3 and 7 over 2. So then they're going to go ahead and take those extra steps to go ahead and factor. And again, those are 3 zeros there. So they actually also did it down below. You can kind of see there. They took each factor, set them equal to 0, and then they actually did a nice thing and they plotted for us. So there is our 0, there is our 4 over 3, so it's like roughly 1.25. And then we have our 3.5, which comes from that 7 over 2. If you want to go ahead and convert these to decimals, all you got to do is enter in the calculator 7 divided by 2. You'll get that decimal 3.5. 4 divided by 3, 1.25. So we found one of the key features for this polynomial, our zeros. Now, the idea is that it's a rough estimate because it is an odd degree power and the coefficient of it is 18, positive 18. That tells me that the right side goes up and the left side is going to go down. So I can kind of roughly estimate it looks something like this. Is it going to look exactly like this? No, but it's a rough estimate. Oops, I just wanted to get rid of my graph. So let's go ahead and continue what other features we can find. Or actually, we're going to go ahead and do this with a problem here. So says use synthetic division to find the zeros of the polynomial function f, then plot the zeros on the graph. So I didn't go over those two, factoring polynomials or synthetic division. Give me a moment. Let's see. So if I go back to slide 22, I'll go back to the question back over there. But synthetic division, we are going to try in the box, write the value of the factor. Write the polynomial expression standard form, each degree, right? Okay. Yeah, they didn't go necessarily. I think it's going to be the guessing game at this point. Yeah. Don't like the guessing game. Okay. Let's go back to that question there. I'm going to go ahead and help you do the setup and we'll go ahead and work on it together here. So, and we'll use some of the numbers here. So use synthetic division to find the zeros. So remember, we need to make sure that our function is in standard form. So all the powers have to be in descending order. So let's go ahead and count it off. I have x to the fourth, to the third, to the 2, that's to the 1, and 0. So it's already in order. So let's set up our synthetic division. So I think we set it up like this. There's a couple of other ways to set it up, but I'm only going to write the coefficient. So no variables are going to be written here. So the coefficient for x to the fourth is an invisible 1. So we'll write the 1 here. We have 3, negative 27. So there's no, because it already goes in order, there's no need to put a 0 in there. Remember, if you're missing a degree, so they didn't have some number x squared, you would have to put a 0 to fill that spot for x squared. Let me try to squeeze it here, 13 and 42. So the next part here is we're going to use numbers here. So just as a just like as a reminder, so I'm going to draw my line here, drop my 1. And you can technically use any of these numbers on the x-axis. I like to start with the smaller ones first. I'm going to try 1, positive 1. Actually, I'll try negative 1 first. So let me try negative 1. So remember, any number that is going below this, this line here will be multiplied by negative 1 to right back at the top. So the first number is dropped 1. 1 times negative 1 is negative 1. 3 minus 1 is positive 2. 2 times negative 1 is negative 2. Negative 27 plus negative 2 is negative 29. Negative 29 times negative 1 is positive 29. 13 plus 29, that is 12. 3, 42. 42 times negative 1 is negative 42. And if you remember, in order for this to be true, to be considered a factor, I need to have a 0. So 42 minus 42 is 0. So x minus 1, it does work. So I'm going to select a point here and put x minus 1. That means I have a factor of x plus 1. So the reason how we get that negative 1, it comes from x plus 1, because if you take that x plus 1 factor, set it equal to 0, your x is going to equal to negative 1. So now that I found a polynomial that has a less degree, because again, this originally started with x to the fourth power. I'm going to start with the power less. X to the third power plus 2x squared minus 29x plus 42. So I can take this new one and set up a new synthetic division and then just again play around with those numbers to go ahead and see it. So we're going to go ahead and do it one more time together here. Let's take a look. Let's try 1. Because, right, we already did negative 1. Let's try 1. But I'm going to write it, set this one up differently. We're going to write the coefficients of this one right here that I'm going to highlight, right? Because you took the polynomial and you're shrinking it down, especially when you have that 0. If it does not equal to 0, you have to restart all over and try a new number. But also make sure you write down the numbers you're using so you don't repeat. So again, let's write out those coefficients. So I have 1, I have the 2, I have negative 29, and I have 42. So I'm going to draw my line here. Let me move this over because I know it's going to pop up. There we go. All right, so I bring down this 1. Keep in mind their coefficients from here. And I'm going to try 1. So 1 times 1 is 1. 2. So remember, up here you're adding 2 plus 1 is 3. 3 times 1 is 3. Negative 29 plus 3 is negative 26. Negative 26 times 1 is negative 26. And I do not get 0 there. I get, what is that? 4 to 30, 12, 16. So 1 did not work. So I'm going to go ahead and make a list of like the ones that I've used. 1 did not work. So I'm going to clean this up and try another number. Let's try 2. So I'm going to try 2 on here. And you just continue until you break it down. So 1 times 2 is 2. 2 plus 2 is 4. 4 times 2 is 8. Negative 29 plus 8 is negative 21. Negative 21 times 2 is negative 42. And I get a 0 there. That works. So my 2 also works. And remember, how do I get that 2? That comes from an x minus 2. So again, as I remember, this originally started as x cubed. This starts 1 power less. So this is x squared plus 4x minus 21. Now, because I already have x squared and we've already done plenty of examples with factoring polynomials, we should go ahead and take a look and just apply the giant x for this. So this is x squared plus 4x minus 21. Remember, our c value goes at the top, so that is negative 21. Our bottom value is 4, right, b, because we do 1 times negative 21, our a times c at the top. So multiply, and then to add. So now for the multiples for 21 is only 7 and 3. So but I have to play around with the negative. So if I add the negative here for 7, negative 7 times 3, negative 21. Negative 7 plus 3 is negative 4. I need positive 4. So my negative can't be with the 7. It's going to go with my 3. 7 times negative 3, negative 21. 7 minus 3, positive 4. So these are my factors. So this is broken down to x plus 7. And then it's x minus 3. So this will go over here. We have x plus 7 and x minus 3. But did you notice I didn't put those factors there? Now, because these are clean factors compared to the last example that we had, remember, x plus 7 will give me negative 7. X minus 3 will give me what? By following that same pattern. So go ahead and take a moment to enter that last 0 for x minus 3. Or if you don't remember that quick little trick, take x minus 3 and set it equal to 0 and solve. So let me write it out here so you can go ahead and write it out to find that other 0. X minus 3 is equal to 0. Get x alone and then enter your number down below. And that's all it's asking for. So it's just asking for the zeros. Moving on to slide 25. So it says we can sketch a rough graph of the function by testing values between the zeros. So remember, this is the same example that we were dealing with. Like I said, it was a little bit icky because the zeros weren't perfect, but they do have them listed for us here. And the idea is that we're going to use that same number line and test out a number that's in between it. So you're not allowed to touch or you're not allowed to use a 0. You're allowed to use a number that's within that 0 type of thing. So right here, I'm going to do them in red because I want them to stand out more. Let me see. Right there. So in these little sections, I'm going to come up with a number. So behind 0, we can say -1. Between 0 and 1.1, I'm going to just go with 1. Again, as long as it's anywhere in between those zeros, it cannot be the 0 though. Between these two, I'm going to just use 2. And after this one, I'm just going to use 4. Now they do give us the interval, and it looks like they tried -1 as well for me. So the idea here is you can do the sign chart or you can plug in the actual value to see if you have a negative or a positive. So I'm going to do the sign chart. And the idea with the sign chart is that you're writing each factor separately. And so like, let me write out the factors. So the first factor is 3x. Second factor is 2x minus 7. And then we have 3x minus 4. And what we're going to go ahead and do here, probably might need to make some space. So we're going to test out -1. We're going to test out 1. We're going to test out 2. And we're going to test out 4. So what I'm going to do is clean this up a little bit here. And the idea is you want to use nice numbers. Use them to your advantage. And this is what I mean by the signs. So this will be the final sign. So let me extend these lines here. And so if I plug in -1 into here, 3 times -1 is going to be -3. So I'm going to put in, because my number is negative, it's going to be a minus there. -2 times -1, -2 minus 7, another negative number. 3 times negative is a -3 minus 4, still a negative number. Again, you're more than welcome to plug in those values and then just get the final number and write the final sign. Again, the sign, you want positive for a plus sign for a positive, negative for a negative, minus for a negative sign. Negative times a negative is a positive, times another negative will give you a negative. Trying 1, we get positive here. 2 minus 7 is negative. 3 times 1 is 3, minus 4, negative. These two negatives will become positive, times another positive is positive. 2 times 3 is positive 6. 2 times 2 is 4, minus 7, still negative. 2 times 3 is 6. 6 minus 4, positive. Now, if I multiply these signs, positive and a negative is a negative. Negative times a positive is still negative. Let's try 4. 3 times 4 is a positive 12. 8 minus 7 is a positive 1. 12 minus 4 is still a positive number. This is all positive. So by those ideas here, the -1 is behind this first 0. This is the second, and this is the third. So this comes from the negative side, and then it passes 0, and it's up in the positive area. Then it touches this 0 and goes to the negative, and then we touch the 0 again to go to the positive. And if you remember, I roughly drew something similar, as in probably not the same shape or same depth of how of each of those little hills, but it's the same extension, similarity to it. So you'll be using the sign chart, and again, that's when, so these are my negatives, right? It was at -1, and this is negative. Do you see this piece is that negative part? From here to here is also negative. And then I have my positive here, and here's my other positive. So then this is positive, and this is my positive. So again, you don't know how far it's going or how deep down, but you do have a rough idea of when it's above the x-axis and when is it below. Same idea here that's happening on slide 26. They're identifying for you when is it considered negative, when is it considered positive. Here it is going from -infinity to 0, and then here they're more limited, from 4/3 to 7/2. Moving on to slide 27. So here specifically, how do they come up with these points? And if you can see, the points are not that friendly, as in there's decimals. What they end up doing here is that they actually took the formula. So you can write out the original, or you can write out the one that you already factored into a graphing calculator, and you can identify the relative extreme values. Now, you can use the graphing tool that's available to you on Edmentum. I personally don't, I'm not a fan of it. I like the Desmos one more. Again, if you type in, if you're on, you can go ahead and open up another tab, open up Google, type in Desmos, a scientific calculator. All you gotta do is type it in here. Now, it does have P of X. I think it should be fine. So let me see. P of X. Actually, we don't want to include P. You're going to take out P of X and you're going to enter it as a Y. Y equals, think, what was the starting point of it? Oops. 18x cubed. So I go over here. I'll type in 18. Now, if you're not familiar with typing in the cubed part, you can type in X. And then what you're going to do is when you look at your keyboard, press the shift and the number 6 button to get that power. That is 18x cubed. 18x cubed minus 63x squared. Or open up this keyboard down at the bottom left corner. And you can even put it in there. So minus 63x. And then here you just click on a squared. If you want another power button and you want to type in the number, you'll just enter the A to B. And go ahead and continue. You can kind of see they're already forming the line, but that's how they came up with those points. They used the graphing calculator for that. Let's take a look at the lesson activity on slide 28. So in this activity, you'll use the key features to determine the graph of the function for x squared minus 13x plus 40 and x squared minus 2x plus 3. So what they are doing for us here is that they gave us a polynomial, but it looks like we can factor more. So let's go ahead and actually factor just a bit more here, and then we're going to answer some questions that you can kind of see that we're looking at. So the first thing we want to do is make sure we factor this completely. And because they're all starting with x squared, I'm going to take the two separate sets of parentheses, and I'm going to use my giant X. So I take my A value is 1, my C is 40. 1 times 40 is 40. My B is negative 13. So I'm going to write out the multiples for 40, starting with 1 and 40. 2 and 20. 3 after the 2, 3 doesn't go into 40, so then I go to 4 and 10, 5 and 8. After 5, 6 doesn't work, neither does 7, 8. Okay, so which pair gives me that that can give me 13? And again, we're just doing setups. I'll go ahead and do this one, but let me set you up for this next one. Right here, you have 1 times 3 is 3. We need negative 2. The multiples for 3 is 1 and 3. So you're going to have to play with 1 and 3. Which one has to carry the negative? So when you add them, you get negative 2. For this one right here, 1 and 40, nowhere to get me to 13 if I add or subtract. Neither does 2 and 20. 4 and 10 will either give me 14 or 6. 5 and 8, perfect. Do you see how in order to get 13, you need to both negative 13, you need both to be negative. So from the first parentheses, we do have x minus 5, x minus 8. And if you took a moment to go ahead and work on this one on your own, the negative has to be carried by the 3. 1 times negative 3. Oh, wait, hold on. I need positive 3. That's unfactorable. Okay, so I made a mistake there, right? Because even if I put the negative here and I erase it from that 3, I still get negative 3 and I can't get a negative 3. So the second parentheses is not factorable. So I just have x squared minus 2x plus 3. This tells me I have a complex number. Not just one, but I have 2 complex numbers. So let's go ahead and select the one that applies to this. X minus 5, x minus 8, x squared minus 2x plus 3. So it looks like it's that second option for me there. We're good. Now part B says, plot the real zeros of the function. So because we already have it factored, you're going to set each one set equal to 0. Now, because we know that the last set of parentheses gives you a complex number, you're going to only focus on the first two. You're going to set it equal to 0. So x minus 5 equals to 0, and x minus 8 is equal to 0. Solve for x. All right, get x alone. Whatever answer you get is what you'll be plotting on the x-axis. Remember, those x-intercepts or zeros are all the same thing that we're finding here. So go ahead and take a moment to do that. I'm going to go ahead and move into part B, or part C, my mistake. Okay, so it says complete the statement by describing the end behaviors. So this is where I want you to go ahead and take a moment to go ahead and practice how to put this into the graphing calculator, because they did touch bases a little bit on that in here in Edmentum. So you can write the original, or again, you can write out the factored. Again, I personally have a preference for the Desmos graphing calculator. Just type it the way you see it's there, right? So I need parentheses. So I have open parentheses, x minus 5, close. I have another set of open parentheses. That's x minus 8. Let me add that so you can see. The next is open parentheses, x to the power of 2. I'm going to bring this down. We have minus 2x plus 3, and we close those up. And you see, I don't even type in y, and I have my polynomial there. So you might have to kind of play around with it a little bit to kind of see the graph there. Now, right there, it looks to me like a straight parabola, but once right here, you have a little loop. Now it's asking, as x approaches negative infinity. So negative infinity on the x-axis is towards the left side. So this is the left side. And as x goes to positive infinity, meaning the right side. What happens if you follow the graph towards the left? Where does it go? To negative infinity or positive infinity? Same thing for the next one, but you're looking towards the right side of the graph. Is it going to negative or positive infinity? Again, go ahead and take a moment. Take a look at the graph. See if you can try to get a better picture of it there by moving the zoom in and out of it. So it says the y-intercept of the function f of x is equal, f of x equals x squared. So the same polynomial. You can do this algebraically, or you can, again, if you already have it graphed, you can go ahead and take a look at the graph. Where is it touching on the y-axis? I'm going to do it algebraically, where if you're looking for your y-intercept, you're setting your x equal to 0. So this will look like this. So it'd be parentheses. This will be 0, right? Because I'm going to use this one right here. 0 minus 5, parentheses. Do you see the zeros is replacing the x? Parentheses. That is 0 squared minus 2 times 0. And we have this plus 3. And if you can go ahead and do it, simplify it as much as and multiply, and then go ahead and enter your value there for part D. Moving on to part E. So now that you have a rough estimate, keep in mind, you're going to select the graph that they came with. Now, if you take a look at it, you want to compare it side by side. Now, one shape might be clearer compared to the other. You want to pick specific points. Like, again, you know that you should have already seen that your, it goes through the zeros 5 and 8. So if you see 5 and 8, between 5 and 8, how deep or how low did your graph dip? You can compare that by looking at the graph here. So if I zoom in here from 5 to 8, that's the 5, there's your 8. It went down all the way to close to negative 80, negative 77. So you see from 5 to 8, this dips down to a little bit close to negative 20, not low enough. 5 to 8, again, that's how you're going to compare to C. You want to look at specific things Maybe the y-intercept doesn't go through, or it does. Or maybe you want to see how high it should go and how low. Again, all of that can be seen if you compare it side by side. Now, it looks a little bit different in terms of shape because one is zoomed in and the other one, it's zoomed out, and also the interval is way more different. So please watch out for that. Select the correct graph. Don't forget to do your self-evaluation, and we are all set with this tutorial. Yeah, we reached the summary. So again, we have a couple of things. We talked about domain, range, when is a function increasing, when is it decreasing, relative maximum and minimums. There might be more than one, depending on the polynomial. What are your y-intercepts? And again, they refer your zeros as your x-intercepts. So please keep in mind that. How do you find your zeros for the polynomials? Make sure you go ahead and factor it completely as much as you can. In some cases, some sets of parentheses will not be factorable because the zero is a complex number, which we are not allowed to graph in this section. Other than that, yeah, we are done with this tutorial.